Let's start from spring mass system. Right, it can be spring mass, or it can be vibration, or it can be circular motion. It can be of anything, but I'm taking the first class. I'm starting with spring mass system. So this is the first one, is the spring mass system. Remember, all of you learn this one once for a lifetime. It should be remembered. Correct? You should not forget any of the steps because it will not be taught you later. Remember carefully. Spring mass system. What is this? Yes, I'm recording it. It's on recording. Yes. So now what you have here, I'm going to take a spring. Remember, this is a spring. It is loaded at one end, and the other end is fixed here. So this is a fixed point or a fixed line, and this I call this as the mean position. As all of you know, the mean position is the position where the displacement is zero. That's called the mean position. Is a spring, and this I call it as a fixed point. Okay, so this is set into sort of up and down motion. It is not swinging anywhere, but rather it is going up and down. Okay, so you just pull it, and then leave. Pull this, and then you let this free so that it will set into a sort of oscillation. That oscillation I call it as a simple harmonic motion. If I pull this one, let's say it is coming down to this one as a maximum we have pulled here, and when you let this free, let it oscillate. What happened here? It will come and then it will cross the mean position. So though it was in this position, after pulling this one, after leaving this, it will overshoot this point and it will go to the other side also. It will go to the other side here like this, right? So it will be set into sort of this kind of oscillation. So at any instant of time, I can take it as X, and this is the maximum amplitude. I call it as A. When you pull this one, there is a force which is acting downwards, that is F is equal to M into G. When the F is equal to M into G is acting here, there will be an upward force. That force is called restoring force. Remember, one is the applied force, other one is the restoring force. Restoring force is the force which is given by the spring. This force must be opposite to this force. Of course, this must be opposite to the displacement also. Which is opposite to displacement? The restoring force is opposite to displacement. This is a displacement. At any instant of time, I can take the position as X also. Like this, I can take. Correct? So there is a displacement here. It is set into up and down motion. Right? A simple equation. But you will get to know the solutions, very nice solutions you'll be getting. That is applicable for any kind of oscillations. It is applicable even for the circular motion. Such importance is there for this equation. Okay. Now, let's go for this is a spring mass system. So spring is here, mass is connected down here. It is set into oscillation. This is a mean position. Okay. So when the mass is going upward, what happened here? The spring gets compressed. The very property of the spring does not want to get compressed. So it has got an opposite direction. So that time it will be acting the opposite direction. Now when it is elongation, it does not allow this to elongate. When it is compressed, it does not want to get compressed also. That kind of compression or elongation is stored in the form of potential energy of the spring. So those things we'll see slowly. We'll derive equation for that also. Okay. So now let's go to this equation. As all of you know, this. So at any instant of time, I will be able to write the equation from Newton's law of motion. Because this is set into motion, so I can use Newton's law of motion. We have the formula F is equal to M into A. I write M into X double dot. I've introduced the term also. Double dot refers to double integration, two integration. So this is a simple formula I've used. F is equal to MA. This force is the applied force, the force what I have written here, F is equal to mg. The same force is here, given here. But there is a force which is acting opposite to it. That force is a restoring force. So now I want to calculate that particular force. So the restoring force acting on the spring. This force Fr is directly proportional to the displacement. More the displacement, more the restoring force, more the opposition it is giving, is self-adjusting. So this is directly proportional to x. But you see, x is going downwards, but F is acting upward. So there must be negative sign. So that is why I call it as a restoring force. So the negative sign shows it opposes the displacement, where negative sign shows that it opposes the displacement. Always, right? It must oppose. That's what we call it as a simple harmonic motion. Correct? Therefore, I can equate this with this equation. So Fr is equal to, I introduce some simple constant here. Let the constant be k into x. This is a proportionality constant I'm being. Later, I'm going to call this constant as a spring constant or force constant. Right? Where, okay, no problem. K is the force constant, or I can call this as a spring constant. Basically, it is a proportionality constant. We realize what it is, right? We try to understand what k is. That's also we are going to see. Okay, so now hope this is clear. Now I come to the other part. I have written k into x, so I want to infer what k is. So k I can write here is equal to f by x, correct? Modulus, if we take it, is f by x. F is Newton, so this must be Newton per meter. Newton per meter. Remember, the unit of this one is Newton per meter. Newton per meter. Remember that, because we want to make use of that one later also. Therefore, this is my first equation from Newton's law. This is from spring equation. Therefore, I can write in equilibrium. At any point, it is in equilibrium during its motion. In equilibrium, this force F must be equal to Fr is equal to F is equal to Fr, correct? Equal to Fr. F is equal to what? M into x double dot is equal to minus of kx. Where minus sign tells you that it is what? It is opposite. Okay. Therefore, I can write this equation x double dot m plus kx is equal to 0, or I can write here x double dot plus k by m divided by m on both sides into x is equal to 0. This is my third equation. Of course, I got the differential equation. This is the second order differential equation. This is x is equal to d square x by dx square. I can also write like this: d square x by dt square plus k by m is into x is equal to 0. So I can write it this way also. Right? Both are differential equation only. I want to slightly improvise this. I want to get some generalized equations for this. Let us see what it is. Do you remember once upon a time I taught you the first or second class, I taught you central force. In that, you would have learned something like that. Like what I write to that point. See, you would have learned that m into x double dot minus r theta dot square. Do you remember is equal to f f translational. You will learn to this one, right? What is this? This part is r theta dot is omega. Theta theta dot is equal to d theta divided by dt is also known as omega. Omega is the angular frequency, right? Angular frequency. So this part is standing as an acceleration. Remember, this is acceleration. Or another acceleration only can be subtracted from this. Okay, so this must be acceleration. Remember, this is acceleration. This is a rotational acceleration. That is A rotational is equal to r theta dot square, or I can write here r omega square is equal to this. Why I have written here? Because I don't want to derive. I will show you this derivation after a while, after some time. Now, time being, I take the acceleration, right? Acceleration is equal to r, which one? Omega square acceleration and the corresponding force Or I can write here, look at this one, this is r omega square. Here, this is acceleration. Remember, this is acceleration. So this should also be acceleration. Together, it must be acceleration. This is dimensionally is an acceleration. So this should also be acceleration together. Only dimensionally, only same quantity, physical quantity can be added or subtracted. Multiplication is possible with any other quantity, but addition subtraction is possible only with this. So if you say here, this is acceleration, so this must be this acceleration. Instead of r, you got x. That's all. But that's what I'm going to write here. I'm going to write, I don't derive this equation. I will show you the derivation a little later. But now I just consider this one. But we know that this value, which one this is similar to, but we know that how we can write here. I can write the equation itself and show it to you that x double dot plus omega square x is equal to 0. We know that already. We know this one. So that is this one. What you have got here is this one. What I have written here is this. But instead of minus sign, I got plus sign. The plus sign has come because of which one? Opposite force. Otherwise, this is the equation. Time being, you remember this equation. You don't have to remember any of these part. Now it is not required. Only this one. Therefore, this is, we know that from general equation, from some general equation of oscillation, we know this one. Therefore, this is 5. Therefore, equation 3 is equal to equation 5. So we can write here omega square is equal to k by m. Omega square is equal to k by m. Therefore, omega can be given as k by m square root. How do I get to this one? If I introduce something like this, they must be dimensionally equal also. Dimensionally. Look at this one. This is acceleration. This is also acceleration. Right? So dimensionally, look at this part. A small addition I'm doing here. Look at this part. Dimensionally, I want to check. See, this is acceleration. So this should also be acceleration. So x double dot must be equal to minus omega square x. So this, what is that? Unit must be equal to this unit. This is acceleration. So L t power minus 2 equal to, you know, minus 1 will not have any dimension. So I take it as omega square only I want to calculate. This is L. So L and L you can cancel out. So omega square must be 1 divided by T2. T power minus 2 is coming. So 1 T power minus 2, this is dimensionally. When it is coming dimensionally, it must be reciprocal of the square of the time period. Later we will see that omega, this is omega square. Correct? Omega is, this is what I've taken is omega square is coming here. Is it right? Omega. So omega must be equal to 1 by T. It is dimensionally. Remember, this is dimensionally. Later, I will show you that omega is equal to 2 pi by T, that much radian per second. So it is coming perfectly. This is dimensional equation, that is this equation. Therefore, this will be k by m should also be 1 by T square. Remember that. K by m should be 1 by t square. From there also you can calculate. That part you will see later. Tell me whether you have understood this one. Then we'll go to the next part.
Excuse me, sir.
Yes.
So when we say equilibrium position, what do we mean by that in this case?
Equilibrium means, okay, I can write, you will be happy if I write like this. Look at this. This is, I've said this is equilibrium. This part I'm writing here. Are you happy? This is equilibrium. The net
Yes,
force
sir.
acting on the
But
body.
sir,
Yes.
sir, I didn't get what this F stands for here. Is this the weight minus applied force, or what is it?
This force is equal to F is applied force minus of the which one restoring force. That must be equal to 0. Sum of these two forces must be equal to 0. That's what very much I used here. Sum of forces must be equal to 0. Because it has become positive because of the restoring force. Other one. Displacement is against. When I say equilibrium, that shows that when I say equilibrium here, the net force acting on the body is 0. That means the upward force, the force what you have here is a downward force, Fr is the upward force. So at any instant of time, suppose the body is here, the upward force must be equal to downward force. That's what I mean. Any other doubt? At what position, one of the students has asked, what position the body is in equilibrium? Every point it is in equilibrium. This point is called a mean position, but during its motion, everywhere the upward force is equal to downward force. Remember that. At every point during its motion, the upward force must be equal to downward force.
So, sir,
Sir,
F is actually distorting force.
Uh, F is called a restoring force. F is called applied force. The other force is restoring backwards. You want to call it the retorting force? No, this is restoring force. It is restoring backwards.
Oh, okay, sir. Okay, thank you.
Yes. Any other doubt? I
Sir,
give the small question to this. Yes, Lydia.
sir, can you explain how you replaced K by M by omega in equation 5?
Okay. This is what you were asking.
Yes, sir.
This part. Look at this one. I hope you understood the third equation and the fourth equation. No problem, right? This is the same thing only I've written here. Now, any general equation, if you want to see for any oscillation, the general equation for the oscillation is coming in terms of the angular frequency. That is x dot plus omega square x is equal to 0. This is a general equation, general well-known equation. Okay. I think you will be able to understand better if I write like this. I thought of introducing it later because since you asked, now I write this part also. Look here. You know the displacement of all of you look for a while. You know the displacement x is equal to, can be given in terms of sine theta, amplitude into sine theta. Is that right? Sine theta, I write it as omega t. This is a general equation for the displacement. Are you okay with this one? Sine theta, last class I told you, it is varying in terms of sine or cosine. Okay, I'm also going to show this one. Now, this is a particle displacement. Now I want to write dx by dt is the velocity. I can write here a sine theta become cos omega t into omega. Correct? You get. Now I want to find out the particle acceleration. So d square x by dt square is equal to a omega as a constant. Cos omega t becomes minus sine omega t into omega. Therefore, you get here minus a omega square into sine omega t is equal to minus of omega square into x equal to d square x by dt square. This is what I had written here. What I have written here is this. Right? X double dot plus omega square x is equal to 0. Are you happy now? This part I just wanted to show to you later. So time being for the differential equation, you remember this equation directly. Later you can derive this part, these derivations. I'll tell you later how it should be derived. So
Sir,
yes,
sir, in the diagram you have written that F equals to mg,
F is equal to mg, correct? Perfect.
and but sir, in the equation it's F equals to ma. So what's the difference?
Look at this one. This is nothing but the force applied to this one. Once you set this one, which one set into oscillation, correct? Now I have written here general equation. This is mg I have written here. So this confuses you in mg. As far as this is concerned, this x will become g. Don't worry. I give another equation in this way. It will be another diagram, so it will be easy for you to understand. A frictionless surface table on which this is in motion. The body is in motion. It goes like this. What is the force acting? F is not equal to mg here. F is equal to m into a. Is that right? M into a. But in this case, F is equal to mg because it is acting under gravity. So this x can be replaced with this one. There is no problem. For your sake, time being, I cancel this one. Okay, fine. This is the diagram I have got. Hope you understood this one. This is a spring.
So sir, F
This
is the
spring.
applied force.
Applied force. This is applied force here. Here in this case it becomes mg, but it's not becoming mg this case because it's sliding on the table, frictionless piston. Good.
So actually in the first diagram, in a spring, if we attach a mass, there will be an elongation at first, and then after applying a force, there will be another elongation. Then.
Look at this one. If you just apply a force, let us say it will be elongated, correct? Let it stand in this position. That is the mean position I'm taking. Whichever position it is elongated after applying the force is this much, correct? Then what do you do? You just pull it. You are giving the force again, pulling, correct? And then you are letting this. Then there is an acceleration which is coming to picture, correct? That acceleration only I'm taking it as x double dot.
So sir, this mean position is after the mass is attached.
Perfect. Yes.
Yes.
Yes, perfect.
Sir, the restoring force it act towards the mean position.
Yeah, it must be acting towards mean position only.
Okay,
That is
sir.
the definition of your simple harmonic motion. Last class, 3 different definitions again. The first definition is restoring force must be directly proportional to the displacement, and it must always be acting towards the mean position.
Okay, sir.
Any other doubt? Good. Lot of doubts are coming. Okay, I just give the revision for this one, then I'll go to the next part. Solutions. That will be also again interesting. That is mathematics involved here. Let's see what I've started here. I have a spring. Initially, it is loaded, but it stands in this position. It is not vibrating. That position is taken to be mean position. Then you give a small force jerk and then leave it. Let it go. Let it oscillate from about the mean position. So it will go down. It will go up like this. So every time there will be an acceleration. Correct? For this force, when you want to call this one, you can write it as mg. But when you just set into oscillation, it will be having with a different other property or property of the spring. Fine. So now what you do here, there is an applied force and it is lifting the applied force every moment. That is important. So now I write here, the force is equal to m into x double dot. And the restoring force which is acting on the spring is always opposing the displacement. So I write opposing the displacement by putting a negative sign. I introduce a constant here. This constant is the force constant because it replaces write that for proportionality constant in terms of force per meter. So I call it as a force constant. So equation 1 must be equation 2 because of the equilibrium. As I told you, it is in equilibrium at all positions. So this value must be equal to this force. So m double dot, where x double dot is nothing but the acceleration of the mass which is going up and down. Remember, okay, is equal to minus k into x. So f m into x double dot plus kx when it is coming here, it is 0, or I can write k by m into x. Now, we have a standard equation. So the standard equation is this x double dot plus omega square x is equal to 0. How did I get the standard equation from this way? We know that the displacement is set into oscillation. It is a sinusoidal wave. A is amplitude, sine of omega t. So with respect to omega t, it is varying. If I differentiate, I get cos omega to omega. Once more, if I differentiate, I get minus omega square x. So this is x double dot. This is, when it comes this side, it will become plus omega square x. So x double dot plus omega square is equal to 0. That equation I have written directly here. Therefore, when I compare this and this here, I get omega is equal to root of k by m. This equation, what I have got here, is a differential equation, which one the 3 and 5 can be called as a differential equation, second order differential equation. Any doubt? It can also be verified dimensionally. Shall I go to the next slide? Okay.
Excuse me, sir.
Look here. Yes.
Sir, just now you said equilibrium is at every point, and if restoring force is varying with displacement, then I think it will the values of applied force and restoring force will change. Like they won't be equal at all the points. So I'm kind of confused in this equilibrium part. What exactly you are trying to say?
If this force, according to you, if this force is greater than this one, it will go on, it will never come back. Yes or no? So there is an opposite force which is given by the spring, which is trying to pull towards this. Correct? So if you feel that the equilibrium disturbs you, you can write at any instant. That is fine. When I say equilibrium, what I mean here, the force, the restoring force at any instant of time balances the applied force. That's what I mean. It does not refer to any mean position, but it refers to both the forces balance at that point. So you will be clear if I write this way. I use this way. Look at this. I write at any instant. You're right. This force must balance this force. Is it okay? Oh.
Yes, sir. Got it.
Fine. We'll go to the next part.
Excuse me, sir.
Yes.
Does this formula hold good for larger displacements?
Whether it holds good for larger displacement, it must hold good for any displacement, but that formula, the spring does not hold good for a longer elongation or longer compression. It has got its own limitation. So within elastic limit, if it is oscillating, it holds good.
Yes, sir. Thank you, sir.
Right. So okay. So the next part here is solutions to simple harmonic motion, to differential equation of SHM. All of you remember, it will take about some 20-25 minutes. You'll be able to derive this equation, understand it better also. It is a 10-mark question. This itself will be asked as 10 marks. Correct? Okay. Now, I do not have anything with me now. All that I have got is only one equation. Right? From that equation, I want to modify and show to you. Look at this. We know that. What is that? X double dot is equal to, as all of you know this one, this is d square x by dt square is equal to d by dt of dx by dt. Simple mathematics. In no time, you can learn this one. Equals to, what I'm going to do here, these are all x double dot. I am going to multiply and divide it by dx on both sides. Dx by dt. Correct? Or I can rearrange this dx by dt into d by dx of dx by dt. Correct? I have grouped this one dx and dt here and d by dx I can do this one. Mathematically, it allows. Equals to, this is your velocity term. This term is velocity, and so this term also velocity. Correct? This velocity. Therefore, I can write here v into d by dx of v equal to x double dot. Instead of keeping it here, can I check whether I can write it this way? Is equal to d by dx of v square by 2. If I differentiate this, I'll be getting this equation. Differentiate and check. Right, if you write something like this, now dv square by 2, you can take 2 1 by 2 outside. dv square is nothing but 2 into v into dv by dx. Correct? 2 will be getting cancelled and you get this. So I can write this equation in this way. Let this be the first equation. Any doubt you have here? So now the second part of it. But
So once more you explain.
we know that. Okay. Look at this part. This is the first equation is the acceleration. Acceleration is the second order differential equation. Acceleration is the first order differential equation is velocity, and the second order differential equation is your acceleration. So d square x by dt square. So d square x by dt square is d by dt of dx by dt. And what I do here, I multiply and divide by divided by x dx, numerator and denominator. Then I group dx and dt here. I have taken dx by dt. This and this I am taking, and this by dx. Mathematics allows this. Therefore, dx into dx by dt. But dx by dt is v. V that we have substituted here into dv by dx. I don't want to write the equation into v into dv by dx. I want to bring that v also inside the differential equation. Correct? Inside differential equation. What will I do here for that? I go for this method, so that will be easy. What I do here? Here I take a d by dt of v square. If I want to differentiate this, the differentiation of this one will become 2v into dv by dx. Is that right? But all that I want is this one, 1 by 2 d by dt of v square is equal to v into dv by dx. That's what I have got here. This is what I have taken here. In this place, v into dv by dx, I have substituted this value, which one? d by dt, v square by 2. I can take 2 outside or inside, no problem. That's what I have written. Hope there is no doubt here. Come to the next part. Okay. The second part of it is, I go to the equation. We know that the general equation is what? X double dot plus omega square x is equal to 0. But x square is this equation. So I write here d by dx of v square by 2 plus omega square x is equal to 0. I want to apply some simple mathematical technique in order to solve this equation. All that we want is, this is in terms of acceleration, I want to reduce this into velocity and then velocity to displacement. This is what I want to do. Equal to this much. What I do here, as I've done earlier, check whether I can do this way. D by dx of v square by 2 plus omega square x square by 2, I can write d by dx is equal to 0. Check whether you are able to understand this one. You have here, what I've done here in this part, look at this part, you take it separately and see omega square x square. If I want to differentiate with respect to x, what I get here, omega is a constant, so omega square is a constant. X square will become 2x into dx by dx. Correct? Dx by dx will get. So this becomes omega. What do you want here is omega square x only. But this will become 1. So I can write here 1 by 2 d by dx of omega square x square is equal to omega square x. So instead of omega square x here, I have substituted this value.
So you have forgotten to write x square in the previous equation.
Is there very much correct? Good. You identified correctly. Perfectly right. Yes. You got this equation. And you got this. Hope you understood this part. Is that easy? Or if you feel that is lengthy, I write once more and show it you. Okay, look at this. What I do, I take now, consider, I take this as the second equation. Consider, what is that? D by dx of omega square x square is equal to, if you consider this one, we want to find out the differentiation of this, equal to omega square is a constant. If you differentiate this, 2x into dx by dx, this becomes 1. Therefore, I want to take omega square x. So 2 is coming down. So d by dx of omega square x square by 2. Omega square x square by 2 is equal to this much. Therefore, equation 2 becomes d by dx of b square by 2 plus d by dx of omega square x square by 2 is equal to 0, or I can write d by dx of b square by 2 plus omega square x square by 2 is equal to 0. Correct? Or you bring the dx to the other side, no problem. It will become 0. So what do you get here? And you get d of b square by 2 plus omega square x square by 2 is equal to 0, because dx you have brought to the other side. Now on integration if you do here of d of b square by 2 plus omega square x square by 2 is equal to 0. So integral of differential equation. So both of them will cancel. So you get here v square by 2 plus omega square x square divided by 2 must be equal to 0. And here it won't come to 0 because there is a constant of integration, because which is there. No limits are given here. So this becomes a constant of equation. I take it as C is a constant of integration, where C is the constant of integration. constant of integration. That should be calculated for boundary condition, which is to be calculated for boundary condition. Boundary condition. I just move to the other side. Boundary condition. Therefore, boundary condition. What is boundary condition? Which should be calculated for boundary condition. What condition when at the extreme position? Extreme position, the velocity is 0. Extreme position, x is equal to a, but velocity equal to 0. You know that when it is vibrating here, when it is going to this one, velocity is equal to 0, but x is equal to a. So, if you substitute, you can calculate c here. Therefore, equation 3 becomes this one. You want to substitute here, right? B becomes 0, 0 by 2 plus omega square a square by 2 is equal to c. Therefore, this anyway becomes 0. C is equal to omega square a square by 2. Therefore, equation 3, now you apply, instead of c, you can apply this value. You will get here b square by 2 plus omega square x square by 2 is equal to omega square a square by 2. So, 2 you can cancel everywhere, and you can write here b square is equal to omega square a square minus omega square x square equals to omega a square minus x square. The square root is equal to b. Here we are getting plus or minus. This is the velocity of the vibrating particle. If you have any doubt, you can ask. This is, I have found out the velocity. Now one more differentiation, if I do it, I'll be getting amplitude. Which one I'll get? I'll get the displacement. Tell me, I repeat this, after that you can ask me if you have any doubt. Okay, look at this. This part. Let's take the first step, first line. X double dot is equal to dx square by dt square. Right, all of you know this is second order differential equation. Correct? That is d by dt of dx by dt. And why I've done dx by dx? Because I want to apply some simple mathematics so that I can reduce the equation. Dx by dx, so that these dx are interchangeable. I can change the variable, put it here, and this variable I can take it here. Dx by dt, d by dx, dx by dt, I can write. But dx by dt is equal to v. Therefore, this becomes v, this becomes v. v into dv by dx. In order to convert this into this form, I go for this one. What is that? D by d of v square I'm taking. By v square I'm taking. If I take this, d by dt of v square equal to 2 into v into dv by dx. dv by dx. The 2 I'm sending it down here to the other side. Half into d by dt of v square equal to v into dx. v into dx, v into dv by dx is the one that I need. v into dv by dx I need. So it has come here. So instead of writing v into dv by dx, I can write this. This has been written here, v square by 2. Therefore, our general equation x double dot plus omega square x is equal to 0. This x double dot I write this here. I take it as a second equation. Now what I have done here, I have taken the second part. Consider this part, omega square x, this one. I have just taken let, right? If I do this one differentiation for omega square x square, I get omega square is a constant anyway, omega square. If I differentiate this 2x into dx by dx, this dx is there, dx by dx. So dx by dx equal to 1. So this 2 comes down, omega square x square by 2 equal to omega square x. So instead of this omega square x, here instead of this, I can substitute this value. That's what I've done here. This is d by dx. This is also d by dx. So I take common here out. So v square by 2 plus omega square x square by 2 is equal to 0. I can take out the 2, it can be 0 here itself. Anyway, I hold it and finally I change it. That way also I can do here. What I do here? Right, fine. Whichever way, no problem. I kept it like this. So I pushed this dx outside. Along with the 2 also I can just send it out. Fine. That way also I can write, so it will be simple. 2 also is common. So when it goes to the other side, it will become 0. So I write that way. So it will be still easy for you to do. This one. Okay, so this is v square plus omega square x square. So then this 2 will not be there. I cancel this. So that I give you a simple equation, that's all. Equal to v square plus omega square x. If I do the differentiation, I'll get only the top term. This will not be there. I get v square plus omega square x square plus c. The c, the term c will come here, where c is the constant of integration. Then I bring it to the other side here. When at the extreme position, so I told you this is to be calculated for the boundary condition. To be calculated for boundary condition. Boundary condition is the extreme condition or initial condition. Initial condition we do not know. So extreme condition we know x equal to a and v is equal to 0 when it is coming to this point. Therefore, this part, anyway, I just replace this one. This term will become 0 and this will not be there. This will not be there. So I make the equation simple. Okay. So what do you get here? This will become omega square a square plus 0. Omega square a square. So c substitute here. You get the omega square x square. Bring it to the other side. You get this equation. This is velocity. You are getting plus or minus sign because the square root of this one you calculate. Take the common and square root you get. Any doubt in this part? I have to do one more write a differential equation for calculating x value, that is the displacement. You remember in the first part I wrote something like this. X is equal to a sine of omega t plus some function, some phase difference, and I have to put this equation I have to bring. This is nothing but a displacement equation. If I spend another 5 minutes and I'll get it. Shall I do it or we can see it next class?
Sir.
Okay, you can ask me some doubt. After that, now we can see. Yes.
Sir.
Yes.
Sir, can you please repeat the red patch thing you wrote in the red patch? I did not get it.
Here?
Yes, sir.
This part?
Yes, one.
This one, right? The red color one, right?
Yes.
Okay. The other one is okay. You are able to understand the other part, right? This part is okay for you, right? Dx by dt, I have brought here like this. Dx, the second dx, this dx is going here. This is coming here. So you got. Now what I do, I write consider d by dx of v square is equal to 2v into dv by dx. Is that right? All that we want is, what do you want? dv by dx I want. Correct? What I do here? 1 by 2 d by dx of v square by 2. I have brought the 2 down here into v into dv by dx. Now, this part, v into dv by dx is the one what you have here. I am replacing this with this equation. D into v square by 2. Hope you understood now. Any other part? Any other doubt? You can ask me. Otherwise, sir, can we obtain the same equation by differentiating? Yes, perfectly. You can do it in the homework also, and you can get it checked today after tomorrow when I come to the next one. So do once more, one more differential equation. one more differential, integrate this one, you will get back that equation. So I can give this as a homework for you. Remember, after this, what you are going to do? After this, you are going to do this part. The part is you integrate again. If you integrate again, I want to get the equation a into sine of omega t plus phi. This is the equation I want now. Right? You take it as a homework and then do it. If you have any doubt, you can ask me next class also. Right? I need another 5-10 minutes to solve this one. I can do it. I have some more concept also, related concept. Anyway, I need a little more time. I'll do it next class. So today we are seeing differential equation and the solution for the velocity. This is a velocity equation. I got the velocity
Sir, I
equation,
have a doubt, sir.
both plus and minus. Yes.
So does the negative and the positive sign of velocity in the final result means the direction of velocity from the mean position?
Perfect. Directional velocity. Yes. This is a vector equation. We are going to see right which equation that I am going to choose now. Right. After integration of this equation, I will get some equation. There I will be getting both the positive value and negative value, and one of them I must choose. I will tell you the reason for all those things. For that, I need another some 20-25 minutes. That's why no, I have not started the question now. Any other part, you can ask me. I have not taken the attendance. Anyway, just to go through this, and you can ask me questions. Before that, please type numbers.
Sir,